Alright, Assalamualaikum. Good morning. Can you hear me?
Waalaikumsalam Sensei, dengar.
Alright, dengar Okay. Still not many joining us. It's okay. It's already time. So let's start our class. Oh, the earlier we start, the earlier we can finish, right? Okay, so for today we will continue Oscillator, chapter 7, the last chapter for this course, which is we focus on electronic device applications, and which is about oscillators. Okay, and okay, so before we have look at the operating, where is it? Have look into operating principle of an oscillator. We have look about the sinusoidal oscillator, right? And then we will have look already about the feedback oscillators. And so today we will look into detail what is the RC feedback oscillators, the relaxation oscillators, or also known as multi-vibrator oscillator. And also inside the multi-vibrator, we have the 555 timer. So we will look into 555 timer and how 555 timer can be used inside the oscillator applications. Yeah. So a little bit recap from previous class. Okay, right. So before we have learned about sinusoidal or feedback oscillator, or also known as harmonic oscillators, yeah, harmonic oscillators. Okay, so if you can see here, so the feedback, the sinusoidal oscillators. Okay, in order for them for the oscillators to sustain, to sustain the signal waveform. Okay, it must to fulfill the Barkhausen criteria, criteria, which is AB A beta or beta A should be equals to 1. Okay, so Barkhausen criteria Barkhausen criteria is the criteria that needed in order to sustain the signal of the output oscillator. Okay, so in order to sustain A beta, okay, A is the gain at this part, at the opium part, and beta is the gain at the feedback. Okay, so A times with beta should be equal to 1. Alright, and also we can say that the VS, the source, which is actually, there is a source here, which is usually a DC source. Okay, VS 1 minus A and beta should be equals to 0. So these both are Barkhausen criteria, okay, to sustain the output signal waveform. It will maintain, it will maintain the amplitude and the frequency as well, yeah. And we have looked before what will happen if the A beta less than 1. Wait, yeah, just take answer here. All right. A beta less than 1 and A beta more than 1. I think you can refer back to our previous notes, yeah. And then we also have a non-sinusoidal or relaxation oscillator, or also known as multi-vibrator oscillator, which is we're going to focus this on today, right? So before we go to the multi-vibrator oscillator, okay, there's a one part inside the sine wave oscillator or sinusoidal oscillator, or also known as harmonic oscillator. It can be divided into two types. Okay, we haven't touched this part yet. Okay, it can be divided into two types, which is the low medium frequency oscillator and also high frequency oscillator. Okay, and we will focus about wind bridge oscillator. Okay, so wind bridge oscillator is can be categorized under low medium frequency oscillator, alright, and also it using the RC network. Okay, later on we're going to look what is RC network. Yeah, RC network also known as RC feedback oscillators. Okay, RC network also known as RC feedback oscillators. Yeah, oscillators. Okay, and it use, okay, RC network, okay, is used for frequency up to, okay, the frequency, okay, usually is up to 1 megahertz. Okay, the frequency usually up into 1 megahertz. Okay, and inside this low medium frequency oscillator, wind bridge is the most widely used, okay, as RC network oscillator. Yeah, wind bridge is the most familiar one. Is the most famous one. Yeah, and there is also high frequency oscillators which can be applied into Colpitt's oscillator, Hartley oscillator, crystal oscillator, and etc. And all of them, okay, high frequency oscillator, they are using the LC network. Okay, so LC network also known as LC feedback oscillators, yeah, or LC feedback oscillators. Okay, and this usually, okay, these types of oscillator is usually used in higher frequency, okay, which is more than the frequency, yeah, is more than 1 megahertz. Okay, it used or it needed a higher frequency to make the oscillation. Okay, and all right. So these are the network. These are the example of two types of oscillator, and we will look into detail what is wind bridge oscillator. Okay, so wind bridge oscillator, okay, using the lead lag feedback. Okay, there's a feedback here. Okay, these are the example of the wind bridge oscillator. Okay, this part is known as feedback network. Okay, this is the feedback, and this, okay, and this feedback network is using the lead lag network. Okay, what is the function of lead lag network? Okay, lead lag network is used to select a specific frequency. Okay, so lead lag able to select the frequency that is need to amplify the signal inside the oscillator. Okay, and right. Oh. Okay, and there is what the gain here. Okay, same as previous. Yeah? Up here there is a gain, right? A, and this is the beta. So the beta is at the feedback gain. Yeah. So the feedback gain for this wind bridge oscillator is at this part. Okay, these are the feedback gain, and these are the amplifying gain for this type of oscillator, which is the amplifying gain is involve resistor 1 and resistor 2. And if you can see resistor 1 and resistor 2, it is actually the connection of voltage divider circuit connection. Yeah. All right. So as mentioned, yeah, voltage divider set the gain to make up the attenuation of the feedback network. Yeah. So must have a gain of exactly 3 as set by R1 and R2 to make up the attenuation. Okay, so later on we're going to look this gain, yeah, this gain, the gain part, yeah, the amplified gain part, which is the A, right? The number, okay, the total number for gain, okay, which is VF or V in over, V out over VF should equals to 3 in order to make the amplifier, in order to have a sustained signal for this amplifier. And this lead-led network or the feedback network should have one third of gain. Yeah, we will look how this can be derived. Yeah. Okay, so these are the weak bridge oscillator. Okay, as mentioned, this is the A part, and this is the B part. Yeah, this is the beta part. Yeah, this is the A part. Okay, so how to calculate the gain A? Okay, so let's first calculate the gain amplified. Yeah, the amplified gain, which is A. Yeah? So if you recall again, what we have learned from op amp, okay, there is a current flow here, and current that flow here. Okay, let's say that the current flow here is I2, and there is also current that flow here. Okay, I minus. So if you look here, okay, if you look here, I1 plus I2 will be equals to I minus part here, yeah, and the inverting part here, I minus. But we have learned, okay, if you recall again what we have learned from op amp. From what we have learned from op amp, current can't flow inside this op amp due to high impedance, right? Due to high impedance. So I minus will be equals to 0, okay, will be equals to 0, okay, so no current can flow inside here, okay, so it will be I1 will be equals to I2, right? So let's derive this, yeah, I1 equals to I2, and how to calculate I1? I1 is 0 minus, let's say at this point, there is a V minus, and at this point we have V positive, right? So 0 minus V minus over R1 equals to, so the current that flow from I2 is V minus with V out, right? V out here, right? V out over R2. Okay, so from what we have learned from op amp also, V minus is equals to V plus, right? V minus is always equals to V plus. So V plus, what is the value of V plus? Oh, you can see there's the value of V plus is same with VF here. Okay, so there is actually VF here. Okay, VF here. So V plus is equals to VF here, all right? So we can replace inside here. Okay, by the way, why here is 0? It is because of there's a ground here, yeah? So there's a 0 minus V minus, yeah, for I1. All right, so let's replace V minus with VF. So it will be 0 minus VF over R1 equals to VF minus V out. Sorry, this is V out here. V out over R2. So if you rearrange this equation, okay, you will get that V output over VF, which is also the gain, yeah? Okay, V output over VF, which is the input, okay, which is also the gain formula, is same with okay, equal to R2 1 plus R2 over R1. Okay, if you rearrange this equation. So these are the formula for gain for A part, yeah? The amplified gain, okay? So the amplified gain A formula is A equals to VO over, sorry, VO over VF, sorry. Okay, this should be VF here. VO over VF equals to 1 plus R2 over R1. Okay, later on, can you try to derive from here how it can be simplified to be like this, right? Okay, so these are the formula for the amplified gain, the amplified gain, which is at this part, yeah? So let's look how to calculate this feedback gain, right? So feedback gain, okay, later. Okay, so this amplified gain, okay, it consists of a parallel connection of capacitor and resistor, and also series connected capacitor and resistor. So this can be the series part, yeah, can be symbolized as Z1, and the parallel part connection can be symbolized as Z2. Okay, so let's look at the lead lag circuit. Okay, so these are also known as lead lag circuit. Yeah, the feedback network, also known as lead lag circuit. Okay, so this value, yeah, this capacitor and resistor value, both of them, even though the connection is different, which is at this part the connection is parallel, and at this part the connection is series. Even though the connection is different, but the value of the capacitor and the resistor usually the same. Okay, usually the same. Okay, so to simplify this, we can rewrite, okay, as the series as Z1, and for the parallel as Z2. Okay, so Z we know that Z is the impedance calculations. So Z1 is equals to the resistor value, the impedance for the resistor, yeah, R, plus with the impedance of the capacitor, which is 1 over j omega C. Okay, so these are the value for Z1. For Z2, since that it is a parallelly connected, so it will be R, okay, it will be 1, this is actually 1 over R plus 1 over 1 j omega C, and then inverse, yeah, it will be inverse. So this is the value impedance for the Z2. And for the VF, okay, for the VF, okay, so for this, yeah, VO and VF to get the gain for this impedance, yeah, beta is always V output over VF, right? VF is the input, yeah. V output over VF, which is yeah, it will be, so VF, yeah, okay, VF, so VF is equals to, okay, the value for VO, okay, you can get the value for VO later on, yeah. So VF, how to find the value of VF? So value of VF is the currents that flow, okay, currents that flow from here, which is you can find using the current later on, which is VO over the total of current Z1 and Z2, yeah, Z1 plus Z2. Okay, so this is the current of flow inside here, and VF is also the voltage at impedance Z2. Okay, so times with voltage at Z2, which is V, which is I, this is the I times Z2. Okay, I times Z2. Okay, so it will be equals to VF. So later on, okay, when you rearrange this equation, you will get that VF actually is equals to Z2. Okay, so this is the value of VF, right? Z2 over Z2 plus Z1 times VO. So when you rearrange this to calculate the beta, the gain beta for this lead lag circuit, yeah, for this feedback, if you rearrange this, you will get this equation. Okay, where if you bring the if you bring the VF to here, okay, if you bring the VF to here, and this part should be here, and you replace all this value of impedance, yeah, Z2 and Z2 plus Z1 with this value, you will get 1 over 3 plus J omega RC minus 1 over omega RC. Okay. Okay. Next, for this gain, yeah, for this feedback gain, okay, for the gain, to make sure, since that there is a J here, so it means that this part is imaginary, right? So it means that this part is imaginary. So to make the gain, okay, to make the gain to be in a real number, okay, to make sure that the gain to be in a real number, the phase shift, okay, to be a real number, the phase shift, yeah, the phase shift should be, okay, should be 0. Okay, these the conditions to make sure that the gain B to be in a real number. So the phase shift should be 0. So what does that mean? It means that this part, okay, the imaginary part should be equals to 0. Okay, wait, yeah, so I share to you, since that I don't have enough space for this, I will share the whiteboard. This one. Okay. Or are you able to see the whiteboard now? Okay, yeah, yes, right. Okay, so let's look here. Allah, man. Wait, yeah. All right. Allah. Okay, so let's calculate how to make sure that the gain B. Okay. How to make sure that, where is my, okay, here. Okay. The gain B to be in a real number, to be in real number, okay? So, as I mentioned just now, okay, so beta is equals to VF over V output, right? Which is 1 over 3 plus J omega RC minus 1 over omega RC. Okay, later on I will accept that. Okay, so to make sure that the gain in a real number, this part, okay, should be equals to 0. So it means that J omega RC minus 1 over omega RC equals to 0. Okay, so since that this is equals to 0, so it will be omega RC equals to 1 over omega RC. Okay, so since that I mentioned just now that all the capacitors and the resistors value at the feedback network usually the same, which is C1, okay, over equals to C2, and R1 is equals to R2. So it will be, this value is same, so it will be omega squared R squared C squared equals to 1. So omega's, okay. So omega squared is equals to 1 over R squared C squared, and this will make omega equals to 1 over RC. And omega, okay, omega is 1 over F, yeah, equals to, omega is equals to 1 over F, yeah. Sorry, omega is, where is the eraser again? Omega is 2 pi, sorry, omega is equals to 2 pi. T is equals to 1 over F. Omega is 2 pi F, so we can replace that. So 2 pi F is equals to 1 over RC, and F, okay, to get the frequency is equals to 1 over 2 pi RC. Okay, so this is how you calculate. Okay, this is how you calculate the frequency for the real the frequency for this feedback network. Okay, admit this one. So let's go back to the slide. Stop presenting here. Let's go back to the slide just now. Oh, share. Okay. So I need to change my window. Okay, right. So that is how this equation, yeah, this equation can be can be derived. Yeah, this is how the equation can be derived. So so therefore beta is equals to VF over V output is equals to 1/3. Yeah, one third. Since that at this part, since that just now, beta is equals to 1/3 plus J omega RC minus 1 omega RC. Since that to get the real number, okay, to be real number, so this is going to be 0. So beta will be 1/3, 1/3. Okay, it will be 1/3. So that's why, in order for this what wind bridge oscillation signal to sustain, it should have it should what it should what it should meet or what you can say, it should fulfill, sorry, it should fulfill the Barkhausen criteria again, which is gain at A times with gain at beta equals to 1. Since that gains at beta, okay, gain at beta is always 1/3. This is always constant, 1/3. Okay, so gain at A, which is at the amplified gain, should be 3. So that's why I mentioned before, if you still remember, I mentioned that this A should be 3 in order for this oscillation for the signal to sustain. Yeah. Okay. Yeah. Okay, let it come again. So yeah, this is what I mentioned just now. To sustain the oscillation, okay, it should meet the Barkhausen criteria. So this is the Barkhausen criteria, okay, which is gain at amplified A times with the beta gain, which is at the feedback gain, should be equals to 1. Since that this beta gain or this feedback gain is always 1/3 for wind bridge network, so it will make that the amplified gain for wind bridge oscillator should be equals to 3. Yeah. So we have calculated just now A for the formula to calculate the amplified gain, which is 1/R2/R1, right? So this 1 plus R2/R1 should equals to 3, where R2/R1, okay, if you minus this part, yeah, R2/R1 should be 2, and the value, okay, if you rearrange this equation, you will get the resistor value, the R2 resistor value. So where is R2 resistor? R2 resistor, which is at this part resistor, yeah, this part resistor. So this R2 resistor will always 2 times with the value of resistor at R1. Okay, the value of resistor at R2 resistor is always 2 times larger, yeah, 2 times larger compared to resistor R1, in order for this gain, the amplified gain, to get 3. Okay, the value to get 3. All right. So let's look at this example first. Okay, let's look at the example 1 first. Okay, for the wind bridge oscillator circuit shown, determine the oscillation frequency. So what you have to calculate inside this circuit is you need to calculate the oscillation frequency, and also you need to identify if the system can begin and sustain. So it's different, yeah? System can begin and sustain. Okay, before that, this is the condition for the wind bridge to sustain. The condition, I forgot to mention, the condition for the wind bridge to begin, which is at first, to start the signal, okay, to begin the signal, yeah? To begin the signal, AB, okay, the value of beta, not value of beta, the value of amplified gain, which is the A part, should be more than 3, okay. When amplified gain, the value of amplified gain is more than 3, so it will increase, yeah? The signal will be larger, 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 and at one point, the signal will be sustained. Okay, will be sustained. Okay, so at this point, yeah, this point we call this is the sustained signal, or sustained system, or sustained waveform. So to get the sustained waveform, A beta should be equals to 1. Okay, but to start the signal, okay, so this is what we call the start up. Okay, to start the oscillation, start up oscillation, A should be A should be more than 3, so it will be A times beta will be more than 1. Okay, A times beta will be more than 1. Okay, it should, yeah, more than 1. If it is less than 1, you can, we have learned before, yeah, if it is A beta less than 1, what will happen to the signal? The signal will dying. It will decreasing, 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 and it will dying. So this is what will happen for A times beta lesser than 1. But when A times beta more than 1, it will increase the signal. Okay, it will increase the signal amplitude, increase. So but we don't want A times beta larger than 1 always. It's only can, we want only at the specific time, which is at the beginning of the oscillation only. All right, and after that it should sustain. Okay, so if we go back to this equation, so the equation asks, identify if the system can begin. So it means that the system can start, the waveform can start up, the oscillation can start up, okay, and the sustain. So sustain the oscillation when R3 is equals to 0. Okay. So to solve this equation, yeah, so there is a potentiometer here. So this is the potentiometer where the maximum value is 1 kilo ohm. The minimum value, okay, the minimum value of this resistor is equals to 0. Okay, so these are the what potentiometer we call, yeah, where we can adjust the resistance value for this device. Yeah. All right, so let's look. So these are this part. Okay, this part is the amplified gain part, which is the A part, and this part is the feedback gain part, yeah, beta. All right. So first, can the system begin and sustain? Okay, first of all, we should make sure, okay, for the system to begin, okay, A should be more than 3, right? Which is this A part should be more than 3. So let's calculate what is the value of A. So A is equals to 1 plus R2 plus R3. So I will not derive this equation from beginning. Okay, I have showed before. Just for this, in this case, there is a additional potentiometer. So it plus R3 over R1. Okay, so at the first condition, the potentiometer value is 0. Okay, when R3 is equals to 0, okay, what is the value for A? So A will be 1 plus 2.7 kilo plus 0 over 1.5 kilo. Okay, 1.5 kilo. So you will get, if you calculate, you will get 2.8. Yeah, the value of A is equals to 2.8. So if you see the value of A, which is at 2.8, it is lesser than 3. So can the system begin? Can the oscillation begin? No, it can't begin. Okay, when the R3 is equals to 0, when the value of potentiometer is 0, the system can't begin. Okay, it can't begin. Okay, because of why? In order for the oscillation to begin, in order for the system to start, it need the value more than 3. And in order to sustain, it need the value to be 3. Yeah, to be 3 at this part. Yeah. So what is the, let's look, let's confirm. What is the value of Barkhausen value for this, what is the value of A times beta value, right? So A times beta is equals to 2.8. So beta value is always 1/3, right? It's always 1/3. So you will get the value of A times beta 0.93, which is AB lesser than 1. So what will happen to the oscillation signal? It will start and it will die. Okay, it will start and it will die like this, since that A times beta is lesser than 1. Okay, why it is dying? Because based from the Barkhausen, and we have done this before in previous class, it will the signal, yeah, will become lesser and lesser and lesser and lesser. It will be dying. Yeah. So what will happen? Okay, what will happen if we change this potentiometer to 3? Okay, so when R3 is equals, this potentiometer into 1 kilo ohm, which is the maximum value of this potentiometer. So when R3 is 1 kilo ohm, okay, so let's calculate the value of A. So A will be 1 plus R2 plus R3, which is 2.7 kilo plus 1 kilo over 1.5 kilo, and you will get the value of A is 3.47. Okay, 3.47. So when the when the potentiometer turn, okay, its value, okay, change its value into the maximum value, which is 1 kilo ohm. So can the system begin? So the oscillation can start. Okay, the oscillation can begin. All right. But next, in order to sustain, how to sustain the oscillation? To sustain the oscillation, we need to maintain this value. We need to maintain this value into 3. However, in order to sustain the oscillation, the value of amplified again should be equals to 3. So how to change that? What is the value of the potentiometer in order to sustain this oscillation? Okay, so what you can do is the value should be 3, right? 1 plus 2.7k plus with the value of R3 over 1.5 kilo, and you will get, in order for the oscillation to sustain, which is A equals to 3, the value of R3 should be 2 times 1.5k minus 2.7k, and you will get the answer. If you calculate, you will get the answer. All right, so these are the value. What is the value? Yeah, 3 minus 2. Oh yeah, so simple. So 0.3 ohm, yeah, 0.3 kilo ohm. Okay, so the minimum value for the potentiometer in order to make sure that the oscillation to sustain should be 0.3 kilo ohm. Okay, 0.3 kilo ohm. So what will happen if the value of potentiometer is more than 0.3? So if the value of the potentiometer, yeah, R3 is more than 0.3 kilo ohm, what will happen? Okay, the oscillation will begin, and then it will keep increasing. It will keep increasing. It will keep increasing, and at this part, it will clip. At this part, it will clip. Why? Actually, if we look into OP amp, there is a VCC positive and minus VCC to control, to be the threshold value for this for this OP amp, right? Which is at this part is actually an OP amp. So this value will be the threshold value for this one, positive VCC. So it will not be more than this value VCC, and this value will not be more than minus VCC value. Okay, so what will happen if there is no voltage applied here? So if then there is no voltage applied here, it will be increasing and keep increasing. Okay, it will be keep increasing. It will keep increasing without clipping. Yeah, without clipping that this. So this clipping, why it's happened? Because there is a VCC and minus VCC. But if there is no minus positive VCC and minus VCC, it will keep increasing and increasing and increasing. It will not be clipping. Okay. All right. So this is what will happen when the potentiometer value is more than 0.3 kilo ohm. Okay. So what will happen when the potential value is at 0.3? So it means that the oscillation will sustain. So the signal will be, this is the startup signal. This will be the startup signal, and the signal will increase until it will sustain. Okay, it will nicely sustain. Okay, it will sustain. All right. So these are the startup to begin the oscillation, and this is the sustained oscillation. This is when A beta is equals to 1, and this is A beta is more than 1, which is the value of A is larger than 3. This is the value of A is equals to 3. Okay? All right, up until here is okay. Is it okay up until here? Is it clear? Any questions up until here? Any questions so far? Are you with me? Okay, I hope no questions. Since that there is no, all right, thank you. Since all still okay, so let's proceed to the next one. All right, so this is finished, yeah, for harmonic or sinusoidal oscillator. Okay, so let's look again. I've mentioned earlier that we have the sinusoidal oscillator, and also we have the non-sinusoidal, or also known of relaxation oscillator, and also known as multi-vibrator. Banyak nama dia, multi-vibrator. Okay, for this part, it's also known as sinusoidal oscillator, feedback oscillator, and harmonic oscillator. Sama saja. Harmonic oscillator, because it will, the waveform is same, yeah, harmonic waveform. So that's why it is also known as harmonic waveform. Okay, so now let's focus on multi-vibrator or relaxation oscillator. Okay, so between these three names, yeah, the most famous one is multi-vibrator or relaxation. It's very rare to use this non-sinusoidal, but just for your extra information, so I just put here as well. Okay, so relaxation oscillator or multi-vibrator oscillator. So relaxation oscillator, okay, use an RC timing circuit and a device that changes state to generate a periodic waveform. So there is a periodic waveform for this for this oscillator here. So this oscillator can employ bistable devices such as, so actually for this oscillator they have a lots of devices, not only bistable, it has bistable, it has also monostable, and it has also a stable oscillators. Yeah, so for bistable devices, so this is the example for bistable devices. We use these bistable devices with the previous that we have learned, which is switches, Smith triggers, okay, logic gates, and also flip-flop. Okay, I think flip-flop is very well known, yeah, flip-flop, to repeatedly change and discharge the capacitor. So there is an involve of capacitor for this multi-vibrator oscillator. Yeah, there is a capacitor that will take part at the inverting of the op amp. Yeah, so it's differ with this previous sinusoidal oscillator, which is if you look at the Wayne bridge, yeah, if you look at the Wayne bridge oscillator, for example, like this, the capacitor usually take part at the feedback part. Okay, but for this multi-vibrator, the capacitor is taking part at this amplified gain, at this amplified part, yeah, at this part, yeah. So it will involve, when there is a capacitor involved, so it will you will play with time for this capacitor to charge and this capacitor to discharge, right? So, since that capacitor can can collect amount of currents for a specific time, right? So it will involve of charging and discharging of this capacitor. So the typical waveform obtained for this method, for this multi-vibrator, usually you can have a waveform of triangular waveform, for example, like this, sawtooth waveform, okay, sawtooth waveform, which is like this, sawtooth waveform, and then exponential waveform, square waveform, and pulses waveform. Yeah, pulses like this, right? Okay, so let's look what are the difference of principle of operation between sinusoidal oscillator and non-sinusoidal oscillator. So for sinusoidal oscillator, we have a positive feedback, okay, and the output signal is feedback to the input phase. Yeah? If you still remember, okay, this is the resistor, and this is the resistor again, and this resistor will feedback to this input again. Oh, sorry, it will feedback at this part. Yeah, okay, will feedback to this input again, right? It is like this. So this the output. So this signal, the output signal, will feedback, will go back into the input and will be amplified again. Okay, and causes the next output to be amplified. All right, since that this is the amplified gain, this is the feedback gain. So the feedback will the output from the oscillator will go to the feedback network, and the feedback network will send or will transmit the signal to the amplified gain again. Yeah, right. So it is like a cycle here, right? So for non-sinusoidal oscillator, their action rely on the time delay. Why is the time delay? Because of involving of capacitor. Okay, because of the involving of capacitor with the charging or discharging of the capacitor through a resistance. Yeah, okay, so it involves a time delay. So it depends on how the capacitor work. Okay, how fast the capacitor can charge and how fast can the capacitor discharge. Okay, if the capacitor can need a long time to charge and discharge, so it will slow the system, yeah, the cycle. Okay, so multi-vibrator or relaxation oscillation, the circuit, okay, it is a circuit with 0, 1, or 2 stable output. Okay, for example, there has a 3 type, okay, which is stable. Okay, so stable types or network, it requires no output. Okay, sorry, no output. I mean, no stable output. Okay, later on we're gonna look what is no stable output, what is one stable output, and what is others. Yeah, we will focus on stable later on. Yeah, which is, it is a free running. Okay, it is a free running oscillation. For monostable, it is also known as one-shot oscillator. Okay, it requires trigger and it requires one stable. It has a one stable output. Okay, it has a one stable output and it requires trigger. For bistable, or also known as flip-flop, okay, which is the famous name is flip-flop, it requires two stable output, and since that two stable output, so it also requires two triggers. Okay, it requires two triggers. Okay, it requires two triggers. So so since that stable, also known as free running, so it means that, yeah, it means that the output can continuous switch to the one stage to another, okay, without delay, without any delay, without any without any delay. For monostable, okay, since that it requires a trigger, so in order for you to change, okay, for you to change from one state to another, for example, from this stage to this stage, you need trigger for it to change the stage. To change the stage of conditions. Yeah. For bistable, okay, since that it has two stable output, so it means that it has two triggers. For example, in order for you to change from this stage to another stage, you need to change the triggers. Yeah. For this, there is a specific triggers, and for this stage also there is a specific triggers. Okay. But in this case, yeah, in this multi-vibrator oscillator, we will focus only for astable, which is the free running oscillator. Okay. Okay, so these are the these are the example of waveform for astable, monostable, and bistable. Okay, so these are the trigger for monostable. Okay, since that it has a one stable output, so it needs one trigger. For bistable, it has two stable output, so it requires two triggers. So what are the function of this trigger? I keep mentioning about trigger. Okay, I'm not sure if you're familiar or not. So this trigger pulse, yeah, this trigger pulse, the function of this trigger pulse will cause, okay, this trigger pulse, okay, will causes the circuit to enter unstable or the next stage here, the next stage condition. Sorry, salah je. Stage condition. Yeah. All right. So for example, for this stable, so no problem, yeah, because the waveform will keep continuing uniformly be the same, yeah. The waveform will continually oscillate uniformly, yeah, like this. But for the monostable, for example, let's say this is the not stable condition. This is the stable condition. So in order for this stage, from the not stable condition to change into stable condition, it requires this trigger, okay, this trigger to push the signal, I mean to trigger the signal to change the stage to be at this point, okay, for some times, and then again this trigger, okay, according to this time, how much the duration of time it will work. Again, after when the time finish at this point, which is the time is finished, right? At this point where the triggers become zero again, so it will change into not stable condition again. Okay, not stable condition again. So it depends from how long the not stable condition time duration. So it will be this long, and then again it will require another, it will meet another another since that this is a pulse, yeah, so this is a pulse, so it means that the pulse will continuously like this, yeah. So then it will meet this trigger again, so it will change into this stable condition again. Okay, so this is how it works for monostable. Yeah, for bistable, it has two pulse. It has two pulse, two trigger pulse. Okay, might be difference, which is one like this, and another one is like this. Let's see, like this, which is larger, which is the time here, time duration here is smaller, and time duration here is bigger. So for bistable, so since that it requires two pulse, okay, so both are in a stable condition. This is stable, okay. So there's this pulse, yeah, this pulse with this trigger pulse will make the signal to enter the stable conditions, yeah, the stable conditions, yeah. Since that there is no, for this monostable, since that there is no trigger for this point, so it, that's why it is called as not stable condition. For this condition, since that there is a trigger pulse, so that's why it is called a stable conditions, yeah. So for this bistable type, since that there is two pulse, two trigger pulse, so both will be stable conditions, yeah. So for example, so this is the signal, okay. For this signal, so it will meet this pulse, yeah. It will meet this pulse first. So it will meet this pulse, since according to this duration time of this pulse, trigger pulse, it will sustain. Okay, it will sustain. And then when this trigger pulse finish, it will meet this trigger pulse, the next trigger pulse. So it will, let's say this is time 1 and this is time 2. So this is time 1 and then it will meet another time 2. So time 2, it depends on how long this trigger pulse work. Okay, so this is time 2. And then when it's finished, it will meet again this trigger pulse, yeah? So it will be time 1 again, okay? So this is how this bistable types works, yeah? So it changes from this trigger to this trigger, from this trigger to this trigger to oscillates the signals, yeah? All right. So usually, for all of this, yeah, usually this is 0. It will use a binary lah, 0, 1, 0, oh, sorry, 0, 1, 0, 1, yeah. Okay, so this is the S-table using IC 555 timer. Okay, 555 timer. So these are the example of the for the device. Okay, it has 8 pins. So the pins, if how to differentiate each pin is by looking at this part, right? So since that the part is here, so the pin number 1 will start from here. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, all right. So so for each pin, yeah. So it is how to draw this circle, it will look like this, yeah. So this is pin number 1, pin number 2, pin number 3, pin number 4, pin number 5, pin number 6, pin number 7. Come. All right. So for this A-stable, okay, for this A-stable, please 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 be careful, okay, for this A-stable, since that A-stable doesn't require any trigger. Okay, we didn't need any trigger for this A-stable types. So pin number 2, okay, which is usually pin number 2 is connected to trigger. Since that in A-stable case, we didn't need any trigger. So it will connect it together. Pin number 2 will connect it together with pin number 6. So this is how you want to identify, or you want to differentiate a stable connection or a stable configuration with other monostable or bistable configurations, yeah, by looking at pin number 2, okay. So if pin number 2 is connected with pin number 6, so it means that this is a stable connection. Pin number 7, okay, pin number 7 is used for discharging, okay, discharging of this capacitor, yeah. So and pin number 8, okay, pin number 8, pin number 8 and pin number 4 will connected to the VCC. There is a positive VCC. Pin number 3 will be the output, yeah. Pin number 5, there is another capacitor which is at the output here, right? And this is how the inside ICC look like, yeah. ICC timer looks like. Okay, so let's go into detail how this circuits look like. Let's go into inside again. Okay, let's look at the inner part of the ICC timer. Okay, IC 555 timer. Sorry. So this is how it looks like. Okay, this is the internal circuit of this 555 timer. Okay, it has a flip flop. Okay, this is the flip flop part. Okay, this is the flip flop. Flip flop. Okay. This is the SR flip flop, and this is two comparator. Okay, there is a two comparator, comparator A, comparator B, CA and CB. Okay, and you can see here pin number 7 here is connected to the BJT. Okay, it's connected to BJT. Okay, pin number 7 is connected to BJT, right? Discharging, yeah. Okay, so BJT here, we're gonna act like a switch. Okay, it will act like a switch instead of amplifier. Okay, come. Instead of amplifier, BJT will act as a switch, yeah, in this 555 timer, all right? And V out depend on, for this V out here, okay, V out here, depend on capacitor voltage. So for you to get V out here, yeah, will depend on this capacitor. Okay, for this capacitor voltage that will go inside this pin number 6 and number 2, and that will pass through for these two comparator, and then will go inside the flip flop. Okay, and you will get this V out. Yeah, so the value of V out will be depending on this charging and discharging of this capacitor. All right, that will go pass through into pin number 2 and pin number 6. Yeah, so there are 3 resistors. If you can see here, there are 3 resistors that connected like a voltage divider here, like a voltage divider connection here. Let's name this as R1, R2, and R3. Yeah, this 3 resistor here that were connected like a voltage divider, and then at this voltage, yeah, let's look at this voltage. This voltage, yeah, this resistor, yeah, is connected into the inverting part of comparator CA. Okay, and this resistor, the same resistor, yeah, at this point, yeah, this point. So let's mention this as VA minus. Okay, since that it is connected at this minus terminal, right? And at this point, since that it is connected at the non-inverting, which is the positive, so let's mention this as VA positive here. Okay, VA positive. Now, this part, yeah, VA minus and VA positive here, we can calculate it. We can calculate this value actually, yeah. And then let's calculate the value of this this VA part and VA minus value, yeah. So for this VA minus, here's my, for this VA minus, it will be R2 plus R3 over R1 plus R2 plus R3 times with the value of VCC value. Okay, times with the value of VCC. Okay, how did I got this? It by using the voltage divider. How to solve the voltage divider? Same, yeah. So since that the value, let's say the value it's given the value is 5 kilo ohm, 5 kilo ohm, 5 kilo ohm. So it will be 10 kilo ohm over 15 kilo ohm times with the VCC. Okay, we don't know what is the value of VCC. So this will be 2/3, right? 2/3 VCC. So the value of VA minus here is always 2/3 from the value of this VCC. Okay, how about the value of VA plus here? So VA plus, for the VA plus, you can see that it is R3 over R1 plus R2 plus R3 times with the VCC. And then it will be, okay, you can insert the value here. So it will be 5 kilo over 15 kilo ohm, and then times with VCC. So it will be 1/3. So value of VA positive here is always 1/3 with the value of this VCC here. Okay, so this will be, okay, this will be the threshold voltage for this comparator. Okay, so this will be the threshold voltage for VA minus. This will be the threshold voltage for VA plus. VA plus, yeah. So if you can look here, so at the VA minus, so these are the threshold voltage, and this is the VA positive for the value of the threshold voltage. Yeah? So why the input waveform is like this? It is because of the charging and discharging of this capacitor time. Okay, so at this point, yeah, at this point, okay, what will happen to the capacitor? The capacitor is charging. So when the capacitor is charging, which is at from zero, from the positive, from the 1/3 of VCC to 2/3 of the VCC, it will, the output, yeah, this is the output. The output will become maximum. Okay, the maximum, but the value of this maximum value will not reach this VCC value. Okay, since that the threshold, it will be the threshold value is only 2/3 from the VCC. Okay, so at this point, so this is when the capacitor is discharging. So this charging point is from the 2/3 VCC until 1/3 VCC. Okay, so this point, it will be the minimum value, okay, of this the output waveform. Yeah, so this we can also known as TH, okay, which is the maximum value. Yeah, also known as TH, which is also known as pulse width. Okay, PW. Okay, this maximum also known as TH, which is also known as pulse width. All right, and this low signal, okay, this low signal is known as TL. Okay, TL. So this is TH and this is TL. So what is the total time of this oscillation? The total time will be equals to TH plus TL. Okay, so that will be the total time of this oscillation. Okay, so let's look what is the value of TH, what is the value of TL. Okay, I don't have enough space here, so I need to use this. All right. So I will change my presenting. I will share this part to all. Okay. So I will share this part. Okay, yes, all right. So TH, yeah, TH is when the capacitor charging, yeah, when the capacitor is charging. So when the capacitor charging, yeah, capacitor charging is from the 1/3 VCC, if you still remember the graph just now, until 2/3 of VCC. This is when the capacitor charging, yeah, towards VCC, yeah, towards VCC value, yeah, towards this VCC value. And since that this based from the graph just now, there is a based from the threshold that we calculate just now, as I mentioned just now also, the charging voltage, yeah, will not equal, the charging voltage of this capacitor will not equal with the VCC value, okay, due to the threshold, due to this threshold value. So the value, okay, the value is 2/3, yeah, the maximum value for the capacitor to charge is 2/3 of VCC for comparator A, yeah? For comparator A. So if you look at the the configuration again, so the capacitor, okay, so the capacitor, okay, the capacitor will charging through, it will pass through the resistor RA and RB, right? RA and RB, because there is a RA here and RB, and then there is a capacitor here, right? If you look at the configuration again. So the capacitor will charging by passing through the resistor RA and RB. So how to calculate the TH value? So the formula is tau, yeah, tau ln VCC minus 1/3 of VCC over VCC minus with the 2/3 of the VCC. Okay, so tau, how to calculate tau? What is the formula to calculate tau? Tau is equals to the RC, resistor and capacitor. All right, so resistor, since that it involves resistor A and resistor B, so resistor here will be RA plus RB times with C. Okay, so if you include this equation inside this equation, so it will be TH, and you simplified it, it will be C, we don't know what is the value of C, RA plus RB. So ln of this will be 1 minus 1 over 3 over 1 minus 2 over 3. So it will be C RA plus RB ln 2. Okay, so if you use your calculator, if you use your calculator to calculate, you will get that TH the value of TH. Oh, I think I have reached the minimum point of this. So let's use next. So the value of TH is equals to 0.693 with the capacitor value time. Sorry. Okay, times with the value of RA, resistor RA plus resistor RB. Okay, so these are the value, or these are the formula how to get the pulse width. The pulse width or the maximum point of the output, yeah, which is TH, yeah, this is TH. This is the this is the what? This is the formula, yeah. 0.693 capacitor value times with RA plus RB. All right. So how about TL? Okay, let's look. Let's use for TL. Okay, for TL. Okay, for TL. Okay, TL is the time. Is the time when the capacitor. When capacitor. Sorry, when capacitor discharge, yeah. Discharge, which is from 2/3 of the VCC until 1/3 of VCC. Okay, towards zero. Yeah, it's towards zero. Okay, through the resistor. Okay, through resistor RB. Okay, for TL. Okay, TL. Be careful that. Okay, that it using, okay, the TL is using the resistor RB, or only through resistor RB. Okay, it's different with TH just now. TH is through resistor RA and RB. Okay, so next. Okay, so how to calculate? Okay, through resistor RB at pin 7, yeah. This resistor RB at pin 7. Okay, so TL, for you to calculate TL, same, tau ln 0, okay, since that there is no minus VCC applied to this configuration, if you realize just now, so it means that 0, yeah, 0 minus 2/3 VCC over 0 minus 1/3 VCC. Okay, so and the value of tau is RC, right? So it will be RB, since only RB resistor involved, RBC, the value of tau. So replace inside here, you will get TL is equals to C resistor RB ln 2. Okay, ln 2. Okay, and then if you use your calculator to calculate the value, so it will be 0.693 capacitor value times with the resistor value. So these are the These are the formula, yeah, to calculate the TL value, and these are the formula to calculate TH value. All right. So for you to get the total time, okay, to get the total time, so TH plus TL, okay, so which is 0.693 CRA plus RB plus with this 0.693 CRB. Okay, you will get the total time of this oscillation. Okay, so since that if you already know the total time, okay, by knowing the total time, okay, by knowing the total time, since which is TH plus TL, okay, so you can, since that frequency is 1 over time, so you can calculate, okay, you can calculate, okay, calculate the duty cycle. Okay, the duty cycle, yeah, cycle, Allah, cycle. The duty cycle, yeah, the duty cycle, which is represent as D. So how to calculate the duty cycle? D is equals to TH over TH plus TL times 100%. Okay, so this is another formula, which is duty cycle for the oscillation. Okay, all right. Up until here is okay. Is it okay up until here? Pening sikit. But later on, I think you can go through again. And okay, all right. So back to here. All right. So these are what we said just now. Okay. Yeah, this is what we said just now. I think it's inside here. Yeah. Okay. So the capacitor C1 is charged from 1 to 3. Okay, and then this is for the TH, and this is for the TL, and then from here, which as I explained just now, and from here you can get the value of T, okay, total time, which is the duration time for the cycles. Yeah, so the duration time will involve one full cycle, which is TH and TL. Yeah, and the total time is plus TH plus TL, and then since that from here you can get the oscillation frequency, which is, to get the frequency is F is equals to 1 over T. Okay, so you know the T, so you just replace here, and then from here also you can calculate the duty cycle. Okay, the duty cycle is one. If you put inside here, it will be like this. Yeah. So these are the formula that you need to remember. Okay, but since that there is no exam, we'll include this this chapter. So perhaps it might be used for your assignment. All right. Okay, so exercise 1. Okay, so let's look at the exercise 1. Determine the oscillation frequency, duty cycle, and pulse width for the square wave signal generated by the S-double using 555 timer showed. And the answer is here. Okay, so the pulse width. Okay, so in order for this, configuration, if it is not mentioned what types of this configuration is, so for you to identify what types, so if you look, pin number 2 and pin number 6 is connected together, so straight away you can know that it is a stable configuration. All right, so from here, first of all, you need to find the you need to find the oscillation frequency, which is FO is equals 1 over T. So you need to get the T. So in order for you to get the T is TH plus TL, right? So first of all, you need to calculate the TH value. So TH value is 0.693 times with the capacitor and RA plus RB, right? So 0.693 times with the capacitor value, which is 0.01 microfarad, and then RA plus RB, which is 15 kilo ohm, 15 kilo, and you will get the answer is 104 microsecond. Okay, and for TL, okay, for TL, since that the formula is 0.693 CRB, so 0.693 C is 0.01 microfarad times with the RB value, which is 10 kilo ohm. So if you calculate it, you will get 69.3 microsecond. Yeah, since that this is time, so that's why it is a second here. So for you to get the total time for this, okay, plus it together, so you will get 0.1733 millisecond. Okay, and then from here you can get the frequency for this system. So 173 millisecond, you will get 5.77 kilohertz, yeah, frequency, yeah, kilohertz. And then from here you can calculate the duty cycle, right? The duty cycle, which is T is equals to TH over TH plus TL times 100. So you can get TH is 104 micro over the total time is 0.1733 3 milli, and then times with 100, that you will get the value of duty cycle is 60%. So if you plot the signal, okay, so the signal will be like this, yeah. Okay, so this will be much more longer compared to this because of the time here is longer compared to this time, yeah. So TH is this, which is 104 microsecond, and TL is this, which is 69.3 microsecond, yeah. So the total oscillation is frequency will be from here to here. Okay, so this is the time. So the total frequency will be F equals 1 over T. Okay. All right. If you look here, okay, another additional information that I want. Actually, we finished. Okay. Another additional information that I want to tell to you. It is hard, yeah. Usually, yeah, it is hard to get duty cycle below 50%. Okay, it is very hard to get duty cycle below 50%. Why? I can't change my pen color, is it? Oh, this way, yeah, yeah. Oh no, tak apa. Okay, it's very hard to get the duty cycle below than 50%. Okay, because of what? Because of value. If you look here, the value of TH is always larger compared to value of TL. Why value of TH is always larger compared to value of TL? Because value of TH, it involves two capacitor. Okay, it involves two, not capacitor. It involves two resistor, RA and RB resistor together. While for TL, yeah, at the lower point, okay, it only involves the RB capacitor, resistor. So that is why the value of TH is always longer compared to value of TL, which is always shorter. Okay, so how to get? So if it is given a task for you, how to get? Okay, if let's say the project asks you how to get the cycle, the duty cycle less than 50%. Okay, what you need to do is you need to add diode. At this part, yeah, you need to add diode. Okay, you can add diode at this part, okay, which is parallel connected to RB. Okay, so by adding diode here, what will happen? Okay, when the capacitor wants to charge, yeah, wants to charge, okay, it will pass through this resistor. Okay, we know currents, right? Currents will always avoid resistor, right? So currents, instead of going inside this resistor, which is the value is which very high, 10 kilo ohm, current will flow through this diode, which is the value of resistor is only 0.7, right? We know the resistance inside diode is around 0.7. So current will flow here and will pass through this RB, okay? So in that case, yeah, to get the duty cycle less than 50%, you will get TH, okay, it will involve only CRA because resistor RB is not involved, and TL 0.693 CRB. So you can see here, yeah, only one resistor involved for the TH. So in this case, okay, you can make the value of TL much bigger compared to value of TH. So if value of TL is larger than value of TH, so you will get the duty cycle less than 50%. Okay, you will get the duty cycle less than 50%. Right? So other than that, we finish. So you perhaps can try this exercise too by your own. Okay, you just have to calculate the value of capacitor, the value of resistor, and resistor RA and RB. The answer is given to you for you to check. Okay, this is just the other way around. Okay, where the frequency is given. So if your frequency is given to you, you can calculate the time. Yeah, right. So, and then duty cycle is given to you. Okay, so from the duty cycle is given to you, so you can also calculate the time from the duty cycle. Since that you know the time, you can find the value of TH, right? 100, yeah. So 60%. So when you know the value of TH, you can find the value of TL, okay? By T minus TH, right? T minus TH. So you get all this value. So you can find the value of a resistor RA by you can find the TL once you know the TL, right? TL is 0.693 C and then RB, right? C and then RB. And then for TH is 0.693 C RA plus RB. So you can use these two equations to solve. Then you can find the value of this capacitor. All right. So okay. So for this one, you can try it by your own. Okay, later on, since that I've told to you that we're gonna have assignment for this chapter, I will post the assignment. This is a group assignment. Okay, this is a group assignment. So this assignment, sekejap and off slideshow later on ya. Tak boleh, sekejap Okay, I'm not presenting. Okay, so since that this is going to be the group assignment, is it okay for you to choose your own group members? Is it okay for you to do that? Or you want me to decide your own group members? How? Sekejap Oh, dah buka dah. which you prefer? Yeah, I already opened my e-learning. So, we choose, okay. Opening sikit Okay, tak apa. Okay, so you want to choose. So wait, I want to see how many members are there inside this, because some of you have dropped the subject. Okay, wait, yeah. I need to look again. So that you can choose. Kejap, apa ni? Okay, this one. Cuba mata ni. Okay, so all together you have how many? All together you have 39. Okay, you have 39. Alhamdulillah. 39. So I want each group to have okay, so the 3 members. Okay, 3 members for each group. Okay, so after class, okay, later on you decide by yourself each members which members that you want to work together. Okay, so each of you should play a role inside to complete this assignment. Okay, this assignment is regarding about simulation. You need to do a simulation. So it is free for you to use any free apps, any free software, or if you have your MATLAB and Simulink, also you can use your MATLAB and Simulink, okay, to solve this task. Okay, it is a simulation that you need to create your own simulation to get the output of the oscillation. All right. So each of you, each member of you should play a role to involve inside this task. Yeah. If your roles is only to write the report, so your marks are gonna be lower. Okay. Later on, I will paste the assignment inside your e-learning. Okay. So your submission for your assignment will be through e-learning as well. And the deadline, okay, the deadline will be, what is the date today? The deadline, I think, for you to do the simulation, 2 weeks. 2 weeks is enough, I think. No need longer. Okay, so the deadline will be on the 29th of June. Yeah, 29th of June. So it will be at the end of this month. Okay, 29th of June, which is before your before your final exam. This one. So your final exam, which is on your final exam will be during week 17, right? So now is week 15, week 16, and then today is week 15, week 16, and week 17. Okay, so during your if you finish faster, you can submit faster so that you can do your revision and your final exam revision earlier. All right. So I will post the assignment by today. Okay, you can look at the assignment by today. So you decide yourself, your group members. Okay, and then try to get any free software to do the simulation. Okay, you can use Simulink, MATLAB, or any other free open software that you can use. All right, is that okay? Any questions? How was our test two? Okay, your test, your test two. I think test two is very easy. Most of you, especially the MOSFET questions, and not the MOSFET, the BJT questions. Many of you got full marks for that. So no need to worry for your test two. Later on, I'm going to give you test two marks. Okay. So, but I'm really happy with your test two because most of you can perform very well. Yes, of course, but the MATLAB file is unnecessary. The necessary one is the report. All the results you should put inside the report. Okay, so the MATLAB file, if you want to submit, is okay. But the most important thing that I want to say is the report. Okay, so what the result that you get from the MATLAB simulation, please put inside the report and conclude all inside the report. Is that okay? So it is unnecessary to give the MATLAB file. But if you can give it, so okay, no problem. All right, so we finish our class until here. So good luck with your report. I will paste your report by today by your through e-learning. So decide by yourself who is your group members. Okay, I don't want to put I mean, I leave to you, your group members. Okay, you will do the assignment together with your group members. So please find the person that you can work together with. Yeah. So I hope you will not have problems. But if you can't find your group member, please let me know. Okay. All right. So that's all for today. Assalamualaikum and thank you.